Hey guys, I was in the middle of making some new experiments here inside of Houdini and Copernicus, where I was assembling a more procedural way of flowers or foliage that I can use in a real-time context. Let's say like making a game art asset for Unreal Engine. Um, and I was gonna go through and just sort of showcase what I've learned along the way and how I can make a setup like this, all with the tools that are provided in this here program. So yeah, let's get started. So I also got to give credit where credit is due. Thank you to Intagma for um, giving out some online resources about the feather petal setup involving these new feather SOP operators that can quickly create these foliage shapes on the fly. So big thank you to them. I took some cues along the way for this process. So initially, I had to start with basic curves. These curve lines here, which are set to NURBS, will be integrated into a feather shape operator, and this will help, you know, tell the program how to draw the initial petal shape for our flower. So after doing that, you can see it's now generated this basic shape. Um, these are all like sort of designed for the way artists can create feathers, but in our case, we can easily translate that into a piece of foliage. Once you know it. So once that's done, I begin to drop down these extra nodes here. I resample the feather. I give it some extra noise just to break up the regularity of it. You can see what that's doing. Um, so with that in mind, I add on a few noises here and some extra scaling along the way to affect certain regions. You can see if I do this, it's sort of translating it along the length of the feather shape. Um, Perhaps so you want your petal to be more noisy at the tip versus the root and so on. Um, and then with all that done, I then just drop down a feather surface node. This will just uh, translate everything into that basic planar geometry that we need. I might smooth it as well, just to ease out any bugs and give it a better normal. Um, and in this case, we're also going to drop down a null just to have some references along the way. Um, and I use this setup here to begin the first phase of the texturing process. So with that shape, we have to drop down an attribute wrangle and translate the vector at P into a vector for the UV that moves the geometry into the same space you would find a Copernicus geo setup. So just makes it the same size, 1, 1, 0. And yeah, along the X and Y tangents. And it's good to go. So I have one phase here. I remesh it down to a size where I have a lot more vertices to work with. And I mask out the edges using unshared edges here. Um, and with that, I also create a new float value called edge. Um, so if I click this on the eye and I visualize the edge attribute, you can see it's creating a soft feather along the edges of my geo. And I'm going to use that to dilate the opacity just somewhat inside of my Copernicus network. And so it's not just a thin, harsh paper cut. It's more of a dithering effect in a sense. Also, I blur that attribute so I get a softer fall off to play with. And I have my null value that I can reference inside of Copernicus. In this case, also, I take a simple planar geometry, I apply UVs, and you can see the UVs are perfect along the 0 to 1 tangents. And if I do this with an attribute copy, I move the attributes from this setup, this perfect plane, onto our geo from before. So you can see now the UVs are following along the curvatures of our geometry. It's very good if you want something that has a more of a organic look, of course. So yeah, that's going to be the end result for our other network here. So if I have that all of that in mind, I'll just drop down a simple Copernicus network here, and I'll get started. It's nothing too fancy. The first phase of this whole process is I start with making the foliage pieces that I can then assemble together. Like let's say I make one petal, I then copy that petal around the circumference of an object, like a ring, and I bake all of that resulting um, asset data onto a texture sheet, and then I can use that baked geometry textures within another Copernicus network, but we'll get to that later. For this first segment, I start with just bringing in the geometry with a SOP import. Same thing goes with the other one. So I bring in my UV null and my edge null from before, and I rasterize the geometry. In this case, I get the alpha, but also I drop down another attribute, and I set it to edge, the float value from before. And for this one, I get the UV. So I have two values to play with here. Of course, the output type has to be set to UV and not mono, and this one is mono. So with that, I start playing with noises. Whirly noise is great. It looks like cellulose, chloroplast type information. So we'll sort of introduce that. I'll remap the values somewhat. As they teach you in school, the mitochondria is the powerhouse of the cell, and so on. But yeah, with that, I then I take the green channel from mono, the RGB to mono node. You can see that if I set the signature to UV and the operation to green, I'm going to mask out the green vector within my UV attribute, and I'm going to use that as a blend with these here rematch values. So I get my fractal noises here, I remap them, and I sort of blend, large shapes with smaller details. You can see I get a mask there. This is then blended in with other noises, and yeah. So I'm playing with these along with the UV mask from before, and then I'm remapping it to get this these sort of vertical strokes, and I can use that within the mask for an RGB ramp. So I get my colors sort of looking like so, and then I blend them together to create those flower petal gradients. So yeah, with those masks, we're able to also create a soft looking bump map with the opacity that we gathered here. You can see that with the edge, I'm really just taking the float edge value from before. I invert it, and I have a mask here. From then on, I just fill it with a white value along the outside. And I'm able to have that soft gradient show through, like so. This is great because we can use this throughout our setup as a mask for all kinds of stuff. So that feathering along the side for our noise could be used with first phase of a normal map. So you drop down a height to normal, and our bump map is like so. Finally, I also take these values and I just remap the opacity like so. I invert it, and I have it my mask. And I can drop that down and tie it into the opacity here. If I want to preview what I'm doing, I have a preview material node, and finally, if I'm satisfied with everything, I'll just drop down a list of raw image outputs. I'll have a folder for them, so I say like $hip, and then texture, base color, roughness, normal map, so on. Everything that is mono based should be, or I should say normal map based, should be set to raw color space conversion, and the base color should be set to bake to open color IO, so it matches the sRGB display. And yeah, and you're pretty much all set. You have your maps ready, locked and loaded. So this next part is totally optional, but if you wish to have your foliage animated in some way or have some control for their posing when you're baking these things down, you can use what's called the KinEffects rig and have your petal skeleton tie into a very quick setup here that we can control. First thing I do there is I feather uncondense it. So I drop down a feather uncondense node and I create a shaft group called shaft. And then I do orient along curve, the target up vector being the y-axis. That way it's moving or curling in the right direction, up and down, basically. I personally fuse it just to make sure all my points are conjoined in the right areas. There's no overlaps. And then I create, with the shaft here, a group name, a group promote. I promote my my primitive shaft group into points with a group promote node, and then I drop down a group by range. I call this group name the upper half of my shaft, and then I I move it to this. So I have my points starting at 0 and ending at 14. So I'm getting the top half of this area here. And this will be like the northern tip of the petal that will be curling up and down depending on your liking. And then finally, I just drop down a rig doctor node to create the rig, and from there you can see every point has a name. This is useful for our KinEffects setup. If I look at the geometry spreadsheet, you can see every one of these has a integer assigned to it, essentially. And I have two separate poses, one that's curled and one that is unfurled, like so. So you can see that once I drop down a skeleton blend, you'll notice that it's animating from one position to another. This is done by keyframing the weight value from 0 to, in my case, 96. And these rig pose nodes, they're very important, of course. That's what allows us to transform the shape to our liking. I have 4 different transformations. The first being, well, the root point here, and just scaling it, the overall shape to a certain value. I then have one for the shaft, one that's for the exterior of the shaft, so basically like the sides of the object. Notice if I play with this value, you see how that's unfurling itself. So I keep it kind of in a curled up budding pose like that, and then that other upper half portion is rotated like so. And really, you just play with these group settings until you get something that is looking like that. And our skeleton blend is going to go into the deform point transforms input for a bone deform node. The first input being the capture proximity node. So you type down capture proximity. capture bone, capture proximity. You can tie in your surface and your rig doctor to the regions, and that'll just use the skeleton and bind it according to the points that are located in your surface geometry node. That way we can get our geometry to deform. And then the second input is the rest position. So this is the standing rest position. That'll go into number 2, and you have our Kinepex rig essentially. Finally, this just helps visualize the whole thing. I'm creating 2 separate groups with this code. Essentially, before a certain frame value, it's going to assign one group, and then once it's equal to that frame value, it's going to assign a new group, and then from there, I use those groups to indicate colors. So it's purple till it reaches this point, and then it transforms into another color, or none in this case. So there's a couple of ways that we can approach this modeling for the overall flower shape. In my case, I used a for each loop to define this array of sorts. So if I drop down a for each primitive, you can see I use this to start with. I changed the method to fetch input. So, and I drop down a meta import node. So that's going to give us what's called a iteration value that can be used to define the steps within the process. So let me just type in like MD6 for instance. This is going to be referenced within our transforms. So if I drop down a transform node from then on, I type down some syntax here. I reference the iteration value, see, iteration, within the transform node by typing in detail, parentheses, quotation, dot dot slash nd, quotation, and then iteration in parentheses and 0. And I also multiply that by a very small amount, like 0.10, for instance. This will, what this does is it's going to sort of raise the shape just a little bit higher alongside its counterparts. So for each petal that's being copied around the ring, it's going to jack it up 0.10 value along the y-axis, and then it's also going to rotate that petal piece by the magic spiral number, which is 137.5, and again, I'm multiplying that times the iteration value. So with this in mind, I'm able to get a shape that is like so. You can see if I start to play with that, what that's doing. So 137.5 is usually the go-to number. You can also play with the scale somewhat just to get some wider looking leaves. And I have this time shift node. This was just for use inside of an animation, but I didn't end up going with that approach. For this process, we're just going to keep it pretty straightforward for baking purposes. You can also try it this way. Instead of doing it with the rotation approach, I can do this even simpler. I just jot down 360 divided by channel quotation NCY, and that's going to give us a channel of integers up here, and it will, with that number, multiply the number of pieces by 7, and then rotate it perfectly within the 360-degree axis. So if it's like 3, it's like, 360 degrees divided by 3, by 4, and so on. This is just very useful if you want something more perfect. And yeah. I love this bit of syntax here. It's very useful according to a number of different operations you can try. Um, and then, yeah, that's another way of going about it there. With our petal model shapes in the correct position, we then move on to just applying a material. Um, so I just drop down a lab's quick material node in my case. This way I can just slap on the JPEG textures that I gathered from the previous COPS setup for each petal. So you can see that, they look uh, not just with the base color, but they have normal map, roughness values, they have the proper opacity textures, and in the means of baking this onto a texture sheet that I can use for a very low poly setup in Unreal, I'm just going to take these values and bake them down in a very traditional way. Of course, you're going to want some kind of piece of geometry to fill up the center region of your flower. In my case, I went with a Phyllotaxis looking approach with the geometry I put together here. This is a shape you can often find inside of nature. Phyllotaxis, kind of like something a bit more like of this nature. And that's something that we can do with, once again, arraying points together. So I'll show you how I went about modeling that. Regarding the Phyllotaxis point generation, our goal is to create a array of points that have a spiral looking like this. To do that, we start with generating points. In my case, I just dropped in a point generate node, and um, I tell it to generate this amount of points over 1,000. They're all in the same position, just overlapping itself. And then using a attribute wrangle, I'm going to drop down a bit of code here, but don't worry, it's not too much here. This will just give us some control and ability to play with the angling of our Phyllotaxis array, as well as the radius and the height. So if I want to generate maybe a bit of volume to it, I can play with these controls. With this code here, our goals are essentially to to write out these controls that allow us to generate the shape at hand. The first thing I'm doing is grabbing the total number of points in the geometry. That gives me a consistent reference, so every point knows where it lives relative to the whole set. And then I take the current point number and normalize it between 0 and 1 with these. That value, which I call u, it's a float. I basically tell it to use u as my growth parameter. Represents progression from the first point in the spiral to the last. And I'm storing that u attribute because it's useful everywhere. You can visualize it, draw color, or reuse it later for animation purposes. It's essentially like time, but like frozen along the point array itself. And then with the angle, this is essentially what makes the Phyllotaxis setup come to life. Each point rotates by a fixed angular offset from the previous one. So by multiplying the angle by the point number, I'm effectively stepping around the circle over and over again. If you set this angle up to something like the golden angle, which in this case is 137.5, you get that sunflower seed distribution where nothing lines up and everything feels evenly packed. And then after that, I calculate the radius. So I instead of just pushing points along linearly, I'm multiplying a base radius by a ramp driven by u. And once I've got the angle and radius, I convert from polar coordinates into x and y using the sine and cosine values here. And that places the points along the spiral in the horizontal plane. Each new point rotates a bit and moves slightly farther from the center. Then I handle the y position on top of that. Instead of tying height to the angle, I tie it to that same normalized u value. that means height increases smoothly from bottom to top, and I can shape it with another ramp. With that all in mind, you can see, I've set my angle here in the first channel to 137.5. I played with the radius somewhat using these controls. It's pretty fun, especially if you set the interpolation to a smoother gradient like monotone cubic or Bezier. It can be very useful. The height, I'm not choosing to use it for the moment. And then at the center, I fuse points that overlap with a simple fuse node. So with this all set up, the next step will be orientation. And this is very important because we need to know how to orient the points once I'm copying objects onto each one. Points by themselves don't have a facing direction, so you need to fix this beforehand before instancing geometry. And we start by creating an identity matrix. This is just a neutral transform, no rotation, no scale, no translation, anything, just a clean slate. And then next we compute the main angular rotation. The angle is based on the same Phyllotaxis logic from before. We just take the per point angle, multiply it by the point number, and subtract 90 degrees. That offset is just to align the forward axis of the instance geometry, so it points outward instead of sideways. We also convert it to radians because vex rotations always expect radians. And after that, we calculate another float called out angle. This is essentially the outward tilt. It's separate from the spiral rotation. It's driven by a user parameter and shaped by a ramp using a normalized U value from before. This lets the orientation change gradually as the spiral grows. Near the base, instances will stay upright, and towards the top they can flare outward or curl around and so on, depending on how the ramp is shaped. The first rotation we apply around is the z-axis. This is important because rotating around z controls how much the instance leans outward relative to the spiral, and that's what kind of gives all of the all these points here, their facing direction. I can just show you what I mean. If I play with these values, let's see what that does. Yeah, so I get more control with how I'm, orientating each value outwards from the center, essentially. And then back to the code over here. Finally, we store the resulting matrix as a 3 at transform attribute. This gives downstream nodes, especially copy to points or instant workflows, the full orientation matrix to work with, and Houdini now knows exactly how to place the points and rotate geometry on each point. So I hope that made sense, and from then on, I can tie in just a bit more control. I throw in some new attributes with size. This just allows me to play with a bit of procedural noise with a p-scale down the line if I so choose, and then I can have this in mind with that new attribute, and I then create another integer value. Petal num is equal to pt num, so now I have a unique petal number according to every point. It has its own unique ID. Of course, we're not using petals, we're using little granular size bits of geo, it doesn't matter. And instead of using the height value from before to control the volume, I just ray project it onto an underlying sphere, like so. I project the points downward. This just helps me get a more smoother operation, and I can then clip that geometry and use it within my high poly setup. But yeah, so from then on, I just copy these spheres, these little shapes that have UVs onto each point. I get my shape, I convert it to geometry, I might subdivide it, get something or high poly. And with a bit of normal operations, I have my center bulb shape. It has some filler geo in the middle for use inside of baking, and we're good to go. So the next step, after we have our high poly meshes and their accompanying texture data, is to assemble all this and to bake it down onto a texture sheet of some kind. And it's a twofold approach. First, I use the old school map baker from Labs, and I then take that information, all the baking diffuse, normal map, opacity, and so on, all this texture data, and I assemble it inside of Copernicus. You can see I'm doing this on a very low poly mesh. If I change it to wires, you can see how I'm just trying to preview what that might look like once I bring it into a scene like Unreal or Unity, for instance. And yeah, that's the next phase of this whole process. So I'll go over that here. To start off with the high poly baking process, it's really a no-brainer. I just center the flower shape we modeled from before with the material already applied, complete normal maps, diffuse, roughness, and so on. I might transform it slightly, and then I bring in the our fancy high poly Phyllotaxis shape with some normals applied and some fuzzy texture jibber jabber over here. All this stuff just to give off like this some basic pollen appearance to it. And then I center that, I transform it, and I just make sure it sits well in the center. And there you go. You have your high poly. So I'll reference that later, but for now I just center the low poly plane along the radius of the high poly, and then I use that as the low poly geometry input, and our high poly goes here inside of the maps baker. I make sure I set it to 2048 or something reasonable like that, and I just check the transfers for all that texture data we need. Also, material ID is pretty important too, because you might want that for masking purposes inside of Copernicus. And then you just press bake or render, and then it shoots out all the textures you need. Moving into cops, we have just diving in here. I just import the textures I get from this baker process. It's just an example. I have my normals, my opacity, and I really just play with the data I have to find like maybe a curvature map or just fix regions with the opacity. Make sure I iron out any bugs from the baking. I also extrapolate boundaries. This is a very useful node to have, especially in a foliage rendering context, because we want our boundaries for the mesh itself to MIP correctly when they're in a real-time context. If you have this black fill along the boundaries, the MIP maps will show that black boundary at a distance inside of your scene. As you get further away as a player or in the rendering camera perspective. So to mitigate that, we just extrapolate boundaries. I tie in my opacity into the fill area, my source being the diffuse, and just pulls all of that away from the edges, every color along the outside. So we get something that is going to condense down in a more effective manner. So yeah, I hope that makes sense. And then I just have my base color, all of my outputs ready to go. I then export everything as a ROP image output, set to a PNG. I just have a folder inside a comp for this version. And I do that for every iteration of my flower. So let's say I have like three different types of flower petals or foliage that I want to have in my texture sheet. I'll just repeat this process with some minor adjustments to the base color or opacity, and size, and so on for those high poly meshes, and then render out three different versions, and then pack them together in the final texture sheet. Finally, this is what a texture sheet might actually look like in the end once you've completed the process of baking all this stuff down and translating it onto a 0 to 1 sheet that it can be referenced inside of a real-time engine. Within each of these blocks of nodes, all I'm really doing is I'm taking the baking data from my previous COP setups, and I'm creating sort of a mass transform approach. So I have, like, for instance, I have everything here. Like, let's say I have a leaf, and then I want to adjust the positioning of that leaf to place it in the right portion of the texture sheet. I get a transform 2D node, so I jot that down. I copy all of the parameters I need to adjust, and I just paste them into the underlying copies here. So, like, I'll go to this initial transform, copy parameter for translate, go into this, translate, paste relative references. That way, if I go back to the master transform and I move it to some degree, the positioning will be the exact same for the other textures. So I don't have to do all this one by one. It's just one transform moves everything, all the textures at the same time. And that's pretty helpful. I mean, compared to, I don't know, doing this inside of Photoshop and working across layers, and it just makes for a more tedious experience in that regard. But I find this to be just a bit more straightforward, at least in my own head. In the midsection area here, I'm really just dropping down one blend node after another, and I'm fetching the outputs from my my texture nulls here. So, like, I reference the stem normals and I add them, or I blend them onto the next blend node, mask it with the opacity for that that portion, and just rinse repeat going forward until I have the completed version I want. And I do the same for roughness and opacity, base color, and making sure at the end I'm able to extrapolate boundaries to mitigate any mip-map errors down the line. And yeah, towards the end I have my outputs, normal, roughness, opacity, and I would just export those as targas and have a preview material on the side just to make sure, it all lines up together nicely. Additionally, you can use a channel join node. This is great if you want to pack your textures comprehensively for use instead of the real-time engine, such as placing, like, roughness and AO or pixel depth offset approaches into one single texture. That's probably a very smart way of going about it. For the time being, I just have, the basics going on. And that is essentially all she wrote. And yeah, thank you for tuning in. And I hope this could have been useful to anyone out there. This has just been a very Copernicus procedural friendly approach to making foliage or natural looking biome assets inside of a single program. No need to go back and forth between other DCCs. Just keep everything in one container. That's always a nice feeling. And if you found this to be useful in any way, please feel free to let me know in the comments or ask a question if you so desire. I'll be sure to get back to you right away, and subscribe if you're interested. I'll be trying to see how I can best integrate this with within my real-time scene going forward with some fancy world position offset techniques and just see how far we can push it. So there you go. Thanks for watching, guys, and hope you take care. I'll see you again soon. Bye-bye.